Welcome to lecture number 8 for ECE 341 Random Processes. In this lecture, we're looking at Bernoulli trials and the binomial distribution. So in this section of the course, we're looking at discrete probability events, events which have an integer number of times. A Bernoulli trial is a random event whose outcome is either true or false. Think of it like a coin flip. It's either heads or tails. It doesn't have to be a coin flip. I could roll a 6-sided die. If I roll a 1, it's a success. Everything else I fail. Or in poker. Here's a MATLAB program that we looked at before. It deals out a random hand in poker and then checks what kind of hand it is. Every time I run this program, I get some hand. In this case, the hand was high card, pair, pair, high card. These are all Bernoulli trials. I either do or I don't get this kind of hand. True or false, black or white. The probability varies with the different types of hands, but it's either happens or doesn't happen. Those are Bernoulli trials. A binomial distribution is n Bernoulli trials. Like I flip 10 coins and count the number of heads. I roll 6 dice, count the number of ones. Or back in our previous programs with Monte Carlo, say you deal out 10 hands of poker and count how many hands were high card, how many were a pair. Or do 100. Okay, this is a binomial distribution. I dealt out 100 hands of poker, 47 were high card. Or eventually, we actually went to a million, 10,000 hands of poker. Here's how many times I got 4 hands out of 10,000 were 4 of a kind. 4970 out of 10,000 were high card. Those are binomial distributions. It's n Bernoulli trials. Now, a couple definitions. In this lecture, P is the probability of a true outcome, a success. So if I'm looking at full houses, that's the probability of getting a full house. 1 minus P is Q. All probabilities add to 1. I either get a heads or tails. It's either success or failure. If the probability of success is P, then the probability of failure has to be 1 minus P, or Q. N is the number of trials, and f of x given n comma P is the probability density function for sample size n with probability of success P. Now, a couple things we'll be talking about later in this lecture. We've got a Bernoulli trial, binomial distribution, and there's another one, hypergeometric. A binomial distribution is like I pull marbles out of a bin and then do replacement. The probability doesn't change with each trial. A hypergeometric is when I don't replace the marbles. In that case, the odds change with each time I draw it. That's a slightly different PDF. The PDF for Bernoulli trial is P to the m, Q to the 1 minus m. A binomial is n choose m, P to the m, Q to the n minus m. And hypergeometric, okay, we'll talk about that later in this lecture. The moment generating function is also known as the z-transform. For Bernoulli trial is q plus p over z. Binomial is q plus p over z to the nth power. The mean is p or n times p. The variance is p times 1 minus p or n times p 1 minus p. So let's start out with the Bernoulli trial. Okay, Bernoulli trial is basically a coin flip. It's either true or false, 1 or 0, success or failure. The probability of a success is P, we'll call that a 1. Probability of a failure is Q, call that 0. And Q has to be 1 minus P because all probabilities add to 1. So this is what the PDF looks like as a bar chart. Probability of a success is P. Failure is 1 minus P. It's either 1 or 0. With only 2 possible outcomes, there are only 2 bars, and I can rewrite this as a delta function. It's Q with the delta of m, that's probability that I get a 0, and P times delta of m minus 1. That's a delta function at plus 1. And note that the mathematics don't care what m represents. In signals and systems, we let m be time. In random processes, m is the number of successes. Again, the math doesn't care. So the math that applies in this class also applies to signals and systems. Anytime you're dealing with a digital filter that uses Z-transforms, in this class, we're using Z-transforms. The math doesn't care. So likewise, we're going to be using the same mathematics that you use in other classes. Now, what you call that math depends upon your major. In statistics, that's called a moment-generating function. In electrical engineering, that's called a Z-transform. I'm going to be using the term Z-transform. It's the same thing that you cover in signals, embedded systems, control systems, digital control. Just different name. If you hear the term moment-generating function, don't be confused. It's the same thing. That's a Z-transform. Recall from the previous lecture, the Z operator means next value. So Z times X is X, one sample in the future. Z inverse is the anti-forward, which is delay. So Z inverse X is delay by one sample. What that means is, on this timeline, if I move forward this way, that's a delay. That's divided by Z. If I move this way, that's multiplied by Z. And normally you can't go backwards in time, so normally you don't multiply by Z. However, delaying is easy. So typically in signals, I always delay. Here, this is just number of events, so it could go either way. What that means is the Z-transform for Bernoulli trial, also known as the moment-generating function, is pretty straightforward. It's Q at k equals 0, P at k equals 1. So this is the delta function at k equals 0, the delta function delayed by 1. That's the Z-transform of a Bernoulli trial. Doing some algebra, I can rewrite this as QZ plus P over Z. Now, the reason these are called moment-generating functions is you can generate different moments with them. And I can find that using Z-transforms. Now, some things we'll want to know are the mean, the variance. The mean is just the average. So the mean, kind of by definition, is the probability of K times K. So the chance of getting 0 points is Q, chance of getting 1 point is P. The average then is add all these up. The average of a binomial distribution is P. What that means, if it costs me, if I get $1 every time I succeed, my expected return is P dollars every time I flip a coin. Now the variance is the distance, the average distance to the mean squared. So mathematically, I can just sum up how far is each number from the mean squared times the probability of that number. For Bernoulli trial, the probability of 0 points is Q. The distance from 0 to the mean is 0 minus P squared. Let's see, the distance from P to the mean squared is 1 minus P. The distance 1 to the mean squared is 1 minus P. Probability of 1 is P. Simplify this, this becomes P times 1 minus P. Again, Q is 1 minus P, or P times Q. That's the variance. Now in MATLAB, I can do Bernoulli trials. In MATLAB, there's the function called rand that generates a random number between 0 and 1. RAND of 10, 1 generates 10 random numbers between 0 and 1. And RANDN generates a random number with a normal or Gaussian distribution. So RANDN we'll be doing later when we get to Gaussian distributions. For now, we're just using rand. If I want to flip 5 coins, what I could do is something like this. In MATLAB, I do something like rand 5, 1. Every time I type that, I get 5 different random numbers. If I flip a coin where the probability of success is 0.7, I just do rand less than 0.7. So what this does is that takes the 5 numbers and returns ones or zeros. Was the first random number less than 0.7, second, third, fourth, fifth. So these will be random flips with a probability of 0.7. And I can change the odds. For example, if I want to have a coin where the odds of a success is 0.1, most of the time I get zeros, occasionally get a 1. For the probability of success to be 0.9, I get mostly ones. Not always, but mostly. If the probability of success is 1, I get all ones. Now, if I want to flip 100 coins and count how many heads I get, I can do something like this. I'm going to generate 100 random numbers. It's true if I'm less than 0.7, 70% chance of a success. That'll generate the 100 numbers. The MATLAB command for average is mean. The average of those ones and zeros is this. I should have a 1 70% of the time. And this is a random function, random process. So I'm going to get a different answer every time. So if I try that, here's the 100 numbers. The mean is 0.75. Try it again, 0.72, 0.73. As the sample size goes to infinity, it becomes 0.7. So that's the mean. The mean is just p times n. The variance should be p times q times n. So if I do, let's just do 100 random numbers. So the variance should just be p times 1 minus p. Roll 100 dice. I get 0.21. Try it again. 0.22. If the sample size goes to infinity, like a million dice, 0.21. So that's for a binomial distribution. And kind of note that this is kind of the definition of probability. As the number of trials goes to infinity, the mean and variance approaches what I calculate. For a given sample, it'll be a little bit different, but that's because this is a random process. So that's kind of a Bernoulli trial. It's either true or it's false, 1 or 0. One assumption with the Bernoulli trial is that it has to be a repeatable event. In which case I just repeat the experiment over and over again. As the number of trials goes to infinity, the percentage of the time that it's a success approaches p. That assumes the event is repeatable. Some events are not repeatable. For example, if I say, what's the chance the Vikings are going to win their home opener? You can bet on that in Vegas, but that's not really a probability. The home opener is not repeatable. It only happens once. What Vegas is really doing is they're trying to set the odds so that half the bets are on one side, half the bets are on the other. If the betting is even, half and half, then what happens is the losers pay the winners, and the house just takes their percentage. House is guaranteed going to make money. Where Vegas gets worried is if all the betting is on one side. If that team actually wins, then Vegas loses money. They've got to cover the bets. So they try to adjust the odds so the money is split evenly. And that's actually a highly skilled job, hiring people to figure out where the odds line should be. That's not really a probability. That's just what does it take to make the betting even. So it's technically not a probability, but just FYI. So that's Bernoulli trial. A binomial distribution is the sum of n Bernoulli trials. Now the probability of getting m heads in n trials is as follows. N choose m, p to the m, q to the n minus m. And there's a couple ways to calculate that. One approach is the enumeration. For example, if I flip the coin 2 times, these are all the different possibilities. There's one way of getting 2 heads, 2 ways of getting 1 heads and 1 tails, one way of getting two tails. So that'd be 1 times p squared, 2 times pq, 1 times q squared. If we go to 3 heads, it becomes 1 way to get 3 heads, 3 ways to get 2 heads, 3 ways to get 1 heads, 1 way to get no heads. So that's 1, 3, 3, 1. This is it. Basically what you're doing is combinatorics. If I have 3 heads and say 2, I've got 3, choose 2. So there's 2 1s. How many ways can I arrange a pattern with 2 1s and a 0 in 3 digits? That's 3 choose 2. That's 3 different ways. That kind of leads to where this comes from. If I want to have, say, 10 dice, and I've got 7 successes, I'm going to have p to the 7th. I got 7 heads. I've got q cubed. I've got 3 tails. And if I have 10 spaces, 3, 4, 5, 6, 7, q, q, q. I've got 10 spaces, choose 7 for where to put the p's. That's 10's choose 7. So that's one way to calculate the probability for binomial distribution throughout the formula. Second way to calculate the probability is convolution. So this is the PDF for a Bernoulli trial. I could rewrite that as sum over k of x of k times delta of m minus k. So what you're doing is I have some function x of k. I've got a delta function. When k equals 0, it's just at the origin, and I sweep it. When I multiply these two together, delta is 0 everywhere except k equals 0, and it's 1 at k equals 0. So that picks out x of 0. When k equals 1, I delay this by 1. I then pick out x of 1. When k equals 2, this moves to the right. I pick out x of 2, and so on. So this is kind of a convoluted way of writing x of k equals x of k. What I can do with that is, instead of convolving x with a delta function, I convolve x with itself. What that does is that sets up all different ways of rolling 2 dice. That's called convolution. And kind of what you're doing is, if this is x of k, that's your binomial distribution. X of m minus k, when k equals 0, is, when m equals 0, is that x of minus k is I flip it. So this gets flipped over here. Then as m increases, I start shifting this to the right. So when m equals 0, I'm at this function, m equals 1, m equals 2. When I multiply these two together and sum at k equals 0, I'll multiply these together and get q squared. So at m equals 0, the answer is q squared. When I shift it right, I get right here. I have q times p plus p times q. So this is going to be 2 pq. When I shift it right again, I get this function. I get p squared. So that's the convolution of q plus p over z involved with itself. So that's the net result. This is the PDF for 2 dice. That's convolution. Now convolution is kind of painful by hand, but fortunately MATLAB has a convolution function built in. It's called conv. So suppose I have this. I've got a coin toss, 30% chance of a tails, 70% chance of a heads. This is the PDF for 1 toss. If I toss the coin 2 times, I get the convolution of x times x. So it's going to give you 0.09, 0.42, 0.49. This is for 2 coin tosses. And what that represents is this is 0 heads, 1 head, 2 heads. Kind of makes sense. 2 heads would be 0.7 squared, 0 heads, 0.3 squared, and that's the remainder. 3 heads would be likewise convolution. Now the reason that works is the Z-transform. Now a property of Z-transforms is when you convolve in the time domain, or probability here, you multiply in the Z-domain. So what's really happening is multiplying polynomials, and multiplying polynomials is convolution. So here is the PDF of a binomial distribution. It's Q plus P over Z. That's the Z-transform. If I do 2 coin tosses, I take that and multiply by the same thing. So putting that over a common denominator, that's just the polynomial QZ plus P over Z times QZ plus P over Z. Or if I keep it as 1 over Z's, that's Q, P over Z, convolved with Q, P over Z. I multiply polynomials. When I do that, I convolve. And to see that, let's do a couple examples. Suppose I want to multiply these 2 polynomials together. 2x squared plus 3x plus 4 times 5x cubed plus 6x squared plus 7x plus 8. Now let's write that as increasing powers of x. So the first one, let's take this guy right here, call that B. This is 8 times 1, 7 times x, 6 times x squared, and 5 times x cubed. So that's this. That matrix represents this polynomial. The other one is going to be increasing powers of x, 2, 3, or 4, 3, 2. It's going to be 4, 3, 2. When I convolve, I take the polynomial, one of them, and flip it. So that 4, 3, 2 flips, becomes 4, 3, 2, going the other way. Now start multiplying and shifting. So when k equals 0, I just multiply these 2 together. I get zeros everywhere, except at 0, I get 32. When I multiply these 2 polynomials together, the zeros term is going to be the 8 times 4, 32. Now let's shift it right by 1. This gets shifted right, the 4 goes over here, 3 comes over, 2 comes over. Now multiply these together. So this is 8 times 1, 7 times x, 6x squared, 5x cubed. I shifted it right by 1. So this is going to be 4 plus 3 times x. Multiply them all together. 8 times 3 is 24 times x. 7 times 4 is 28 times x. Add them all together, I get 52. So with one shift, that becomes 52. With one shift, 52x. That's kind of what you do here. I would do 4 times 7 plus 8 times 3. That's 4 times 7 plus 8 times 3. Those are the x terms. To get the x squared terms, I take this and shift it right again. So again, this is 1x, x squared, x cubed. This is 1x, x squared. Multiply these together, I get x squares. 2 times 8 plus 3 times 7 plus 6 times 4 is 61. So there's 61 x squared. Shift again. So this becomes 1x, x squared. This is 1x, x squared, x cubed. Multiply these together, I get x cubes. These will be the cubic terms. 7 times 2 plus 6 times 3 plus 5 times 4 is 52. I get 52 x cubes. Shift again. Keep on going and get all the terms. In MATLAB, that's the command convolve. So here's my polynomial for A, increasing powers of x. Polynomial for B, in increasing powers of x. Convolve the two, there's my answer. And what this means, these are the ones, x, x squared, x cubed, x to the fourth, x to the fifth. So the product of a times b is 32 plus 52x plus 61x squared plus 52x cubed plus 27x to the fourth plus 10x to the fifth. When you multiply polynomials, you're really doing convolution. And that applies to the Bernoulli trials because the z-transform of a Bernoulli trial is this. Multiply them all together, I get q squared, 2 p times q over z, p squared over z squared. Or in MATLAB, if this is a single coin flip, probability of tails, a heads. To involve it, I get 2 coin flips. Here's 0 heads, 1 head, 2 heads. To involve that answer with x, I get 3 coin flips. 0, 1, 2, 3. To involve that with another x, I get 4 flips, 5 flips, 6 flips. That's just using the convolve function in MATLAB. Easy way to multiply polynomials, easy way to combine Bernoulli trials. So that's one way to calculate the probability of getting n flips in 6 trials. Use convolution. Second approach is use the equation. If I want to know what's the chance of getting 4 heads in 6 flips, that'd be 6 flips, choose 4, 0.7 to the fourth, 0.3 to the squared, 0.32415. Go back to convolution. In 6 flips, the chance of getting 4 heads is right here, 0.324135. Same answer. Second way of doing it. And kind of a sidelight. There's kind of a neat pattern when I do n choose m. It follows this pattern. The first row is 1 choose 1. The second row is I have 2 elements. Two choose 0, that's this row. 2 choose 1, 2 choose 2. That'd be 2 coin flips, 1, 2, 1. The third row are the combinations of 3 choose 0 is 1, 3 choose 1, 3 choose 2, 3 choose 3. 4 choose 1, 4 choose 2, 4 choose 3, 4 choose 4. No. 0, 1, 2, 3, 4. 4 choose 4 is right here. That's Pascal's triangle. Another way to do that is for each row, I take the previous row, 1 comes over, 1 plus 1 is 2, 1 comes over. Next row, 1 comes over, 1 plus 2 is 3, 2 plus 1 is 3, 1 is 1. Next row, 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4. That's Pascal's triangle. If you shade in the even numbers as black, actually the odd numbers as black, the even numbers as white, you get this shape. That's called Sapirski's triangle, or Pascal's triangle. How that's useful, I don't really know, but it's kind of neat. Now, one thing to note with binomial distributions is I approach a shape that you see over and over again called a normal distribution. This is a bell-shaped curve. We're going to see that over and over again in this class. It's probably the most important distribution in all statistics. What the central limit theorem states is that under very general assumptions, all distributions converge to a normal distribution. And we can see that with the binomial trial. A single coin flip is clearly not a normal distribution, but flip a coin 100 times and then do a bar graph. This is the frequency of each number for 100 coin flips. I get this nice bell-shaped curve. We see that over and over again. Keep seeing it. That's a normal distribution. So we're going to cover that later in the course, but we keep on seeing that. A couple other things to note with a binomial distribution. All probabilities add to 1. If I flip 100 coins, I get something. The mean of a binomial distribution is n times p. So if I have 100 coin flips, probability of a heads is 0.7, I should get 70, something close, not exact because it's random, but it should converge to n times p. And the variance is n times p times q, which is 21. Now, sometimes with binomial distributions, I have multiple outcomes. So suppose I have two people playing tennis, and it's a best-of-7 series, meaning the first to win 4 games wins the match. What's the probability A is going to win the match? Well, one way to do this is to play 7 games always, and add up the probability that A wins 4 games out of 7, 5 out of 7, 6 out of 7, or 7 out of 7. Now, actually, the way the series goes is once A wins 4 games, the series is over. But it's the same probability as you always play 7 games. Those are binomial distributions. So if A has a 60% chance of winning in any given game, the probability that A goes 4 and 3 is 29%. 5 and 2, 26%. 6 and 1, 13%. 7 and 0, 2.8%. Add them all up, I get 0.7102. So if I have a best of 5 series, A has a 71% chance of winning the series, given that A's got a 60% chance of winning any given game. That's a binomial distribution. A different problem is instead of having to win 4 games, if I have to win by 4 games, or win by 2 games. Now in that type of format, if A wins, then B wins, A wins, then B wins, you're back where you started. That could be an infinite sequence. This is a totally different problem. We can't use a binomial distribution to solve that problem. We need a different tool. That tool is a Markov chain that comes up later in the semester. So winning by 2 is very different than winning 2. Now, one problem with the binomial distribution is sometimes the numbers get really large. For example, back when we did Monte Carlo simulations, we dealt 100,000 hands of poker and counted. How many times did you get a straight flush, 4 of a kind, full house, and so on? These are actually binomial distributions. P is the probability of each type of hand. N is the number of hands dealt, in this case 100,000. And M is the number of hands you get of each type, like 2, straight flushes, 30, 4 of a kinds, and so on. So for example, I just dealt 100,000 hands of poker, and I got 2 straight flushes. That's a binomial distribution, 100,000 hands, 2 successes. Each time I run this, I get a different answer. For example, this time I got 3 straight flushes. Next time I run it, I'll get a different answer. How do I calculate the probability of getting 0, 1, 2, and so on straight flushes? Well, again, the binomial distribution doesn't work terribly well because I have 100,000 choose x. I've got 100,000 factorial. That's a big number. There's a thing called a Poisson approximation. This is a way to approximate a binomial distribution. The PDF for a Poisson approximation is 1 over x factorial lambda to the x e to the minus lambda, where lambda is the expected frequency, n times p. So for example, if I want to have a straight flush or royal flush, n times p is 100,000 hands. Here's the probability of a straight flush or royal flush. Multiply them all together, I get 1.53. So the PDF for the number of straight flushes, royal flushes, looks like this. So there's about a 22% chance I'll have 0 straight flushes and 100,000 hands. About a 34% chance of 1, 25% chance of 2, and 12% chance of 3, and so on. And that's kind of what we're seeing over here in MATLAB. Every time I run this code, I get a different number of straight flushes and royal flushes. Typically it's 0, 1, 2, or 3. I might get lucky, occasionally get 4. That's a binomial distribution, or roughly a Poisson distribution. Now let's do one more example. It's a hypergeometric distribution. Suppose I've got a box full of marbles. It contains A, white marbles, and B, black marbles. Now, each trial, I'm going to reach into the bin, shuffle them around, draw one marble out at random. If the marble is white, I call that a success. Black, call that a failure. I then put the marble back in the bin and shuffle it. What's the probability of drawing X white marbles in N draws? That's actually binomial distribution. Since I put the marble back, the odds don't change. The probability of drawing a white marble in any draw is just A over A plus B, where A is the number of white marbles. And since the probabilities don't change, here's the probability of drawing X white marbles in N draws. That's a binomial distribution. Slightly different is, suppose I've got a bunch of white and black marbles. I reach in the bin, grab a marble, and see what it is. It was this one, it's white. I then discard it. So that marble is no longer in the bin. I then reach in, of the remaining marbles, draw one, suppose it's another white one. As I draw marbles, the odds are changing. This is a different problem. This is sampling without replacement. If you sample without replacement, that's no longer binomial distribution. That's actually a hypergeometric distribution. With a hypergeometric distribution, the number of ways I can draw X white marbles is A choose X. The number of ways I can draw N minus X black marbles is B choose N minus X. The number of ways I can draw N marbles is A plus B over N. So for example, if I have a bowl containing 18 marbles, 8 white, 10 black, and I draw 5 marbles, what's the chance of getting 3 white and 2 black? The probability is there's 8 white marbles, choose 3. There's 10 black marbles, choose 2. Divided by the total number of ways I can draw 5 marbles, 18, choose 5. That winds up being 29%. That's a hypergeometric distribution. So that's kind of what a Bernoulli trial and binomial distribution are. We've been doing that throughout the semester with the Markov or Monte Carlo simulations. Those are technically binomial distributions. A Bernoulli trial has 2 possible outcomes: heads or tails, true or false. I roll a 1 or I don't roll a 1. I'm delta full house or not delta full house. Those are Bernoulli trials. A binomial distribution is the number of successes in n Bernoulli trials. And the equation for it is n choose k, p to the k, q to the n minus k. I can combine Bernoulli trials using convolution or z-transforms. The resulting PDF quickly becomes a bell-shaped curve. That's a normal distribution. That's the central limit theorem in action, something we'll be talking about later. And when you combine distributions, the means add and the variance adds. So that's lecture number 8 for ECE 341, Random Processes.